Alright, last day of curve sketching, we are again going to look at rational functions, which means when we first find the domain, we need to see are there any vertical asymptotes, and that involves us looking at the denominator. Here our denominator is x squared plus 4, so actually no, there's not any vertical asymptotes. That's always going to exist, so again, negative infinity to positive infinity is our domain. For our end behavior, we have to figure out what kind of a horizontal asymptote we have. So horizontal asymptote at, well, what is the degree of our numerator? It is 1, and the degree of our denominator is 2. So since the numerator's degree is less than the denominator, that means we have a horizontal asymptote at y equals 0. Okay, y-intercept, plug in x equals 0. And what do we get? We get 0 also. X-intercept, we need to set our numerator equal to 0 and solve, and that's pretty simple because here it's just 0, 0. Alright, now we are going to find out the intervals where our function is increasing, where our function is decreasing, if we have any maximums and where, and if we have any minimums and where. And that's a first derivative test, so we need to find our first derivative. And to do that, we are going to have to do quotient rule. So derivative of the numerator is 1, denominator is 2x, so let's plug into quotient rule. F prime of x equals, low d high is actually just going to be x squared plus 4, minus high d low is going to be 2x squared, all over low squared, so all over x squared plus 4 quantity squared. And when I do x squared minus 2x squared, that's negative x squared, but I'm going to just go ahead and factor out a negative for right now. So I can write that x squared minus 4 in the parentheses. All over x squared plus 4 quantity squared. So, well, to find my fence posts, I have to find my critical numbers. So is there anywhere this derivative does not exist? No, the denominator is x squared plus 4, it exists everywhere. Is there anywhere this derivative is equal to 0? Yes, that is at plus and minus 2, setting the numerator equal to 0 and solving. So plus and minus 2 are my fence posts. So one at negative 2, one at positive 2. And let's test negative 3. So again, the denominator, x squared plus 4 squared, always positive. I don't really care about that, just the numerator. So if I plug in negative 3, I get 9 minus 4. Then I take the opposite of that. So that's negative and first derivative, so it means it's decreasing. Let's try 0. If I plug in 0, I'm going to get a positive, so increasing. And if I plug in, oops, can't do 2, my fence post is 2. Let's do 3. If I plug in 3, I'm also going to get a negative, so decreasing. So we go from decreasing to increasing and then decreasing again. So it looks like we have a minimum here. Whoa. Minimum. Decreasing to increasing. And then increasing to decreasing, that'll be a max. So intervals where we are increasing just between negative 2 and positive 2. Decreasing from negative infinity to negative 2. And from 2 to infinity. We have one maximum at 2. That's a point on our graph, so how do we figure out where that y value is? We have to plug in 2 to the original function, and it turns out to be a 4th. Minimum at negative 2. So again, a point on our graph. To figure out the y value, we plug in negative 2 to the original, and that will be negative 1/4. Negative there. Okay, now I need to figure out where is my graph concave up, where's my graph concave down, and do I have any inflection points? And that's a second derivative test. So I will rewrite my first derivative, and I'm going to write it with that negative distributed, so negative x squared plus 4. all over my denominator. Let's leave that x squared plus 4 quantity squared. So this is a quotient rule, so derivative of the top is negative 2x. Denominator, you use chain rule to get 4x times x squared plus 4. So we need to do quotient rule here. So f prime of, or f double prime, this is our second derivative of x, equals low d high, negative 2x times x squared plus 4 quantity squared, minus high d low, so that's going to be negative x squared plus 4 times 4x times x squared plus 4, all over low squared, that's x squared plus 4 now to the fourth. So again, do not multiply this out. Notice that we have the x squared plus 4 in each of our terms, so we can cancel out this term entirely. Bring this down to a power 1, bring this down to a power of 3, and then do some multiplication. F double prime of x equals, multiplying in my negative 2, I get negative 2x to the third minus, negative 2x to the third minus 8x. And then this x squared plus 4 is gone, so we have a 4x, and the negative we're distributing in, that's going to be a plus 4x to the third. And then that's going to be a minus 16x all over x squared plus 4 to the third. So let me just do some simplifying here. 4x to the third minus 2x to the third, that's going to be 2x to the third. So f double prime 2x to the third. Negative 8x minus 16x should be a negative 24x. And I can do even more simplifying here. I can factor out a 2x to get x squared. What is that going to be? Minus 12. So now I need to find my fence posts. One of them I know is going to be 0 from the 2x factor. The other ones, if I solve the other factor, are going to be plus and minus root 12, which you can write as root 12, or it is simplified to negative 2 square root of 3 and 2 square root of 3. So about what is the square root of 12? It's about 3.5. So in this first interval, let's try negative 4. Well, again, very nice here because my denominator, x squared plus 4 quantity cubed, is always positive. So I'm really only concerned with my numerator. If I plug in negative 4, let's see, that's going to give me 16 minus 12. That's going to be positive 4, but then I multiply by negative 8. So I get negative. Second derivative, that means concave down. Let's try x equals minus 1 in the next piece. That is going to be a negative times a negative, so positive, concave up. X equals positive 1, that is going to be a negative, so concave down. And x equals positive 4 will be positive, concave up. So intervals where we are concave up, negative 2 root 3 to 0, and also 2 root 3 to infinity. And then concave down, negative infinity to negative 2 root 3, and 0 to 2 root 3. And inflection points, I've got 1, 2, 3 of them. There are 3 places where concavity changes. So I have to find those ordered pairs. The first one is at negative 2 square root of 3, and it's a point on my graph. So to get the actual y value, I have to plug that into the original function. And that's going to be about negative 0.2. And then the next inflection point is at 0, and if I plug that into my original, that's just 0. And then the last one is at positive 2 root 3, which I have to plug that into my original to get the y value, and that's about positive 0.2. Okay, so now let's put it all together and let's graph. And And we've got small y values, so again, let's scale y by 1/10 or 0.1, and let's just keep x regular at 1. So we had a y-intercept and our x-intercept was at 0, 0, and that's one of our inflection points as well. A maximum at 2, positive 1/4. So 1/4 is 0.25, so that's going to be right there. A negative at negative 2, and then negative 1/4, so that's negative 0.25. It's right there. And inflection points, negative 2 square root of 3, that's about negative 3.5. And negative 0.2 will be right there. And then other inflection point at positive 2 root 3, about positive 3.5. And positive 0.2. And remember, we had a horizontal asymptote at y equals 0, so in the long run it's leveling out at our x-axis. Okay, so what is happening first? Well, first our function is decreasing up until the negative 2, so up until the minimum, and it is going to be concave down to that inflection point. So maybe something like this, concave down, decreasing. And then we are going to be concave up between our inflection point and 0, and it's going to be decreasing to the minimum and then turn around and increase. So there's concave up, turning around and increasing. And then still increasing, but now concave down. So increasing but concave down. And then turn around and, well, we're still actually going to be concave down until here, but decreasing now. And then now we turn, still decreasing, but we're going to be facing up, concave up. So our graph will look something like that.